Okay. All right. So the first computer was launched in 1946 at the University of Pennsylvania, and it was developed by a team of researchers, not only from Penn, but also from the Navy, so that they can compute missile trajectories during World War II. It was called the ENIAC, and it was something called a vacuum tube computer. So this is what a vacuum tube looks like. And as you can see, it's kind of like a light bulb. And when you have electricity flowing through it, it represents a 1. When you have no electricity, it represents a 0. And from that, you get your binary math that operates your computers. In the 1950s, a professor from Caltech named Richard Feynman basically said, hey, you're all building really big things. It's a space race. You're trying to go to the moon. How about instead we build things really small? And the examples he gave were, can we write the full history, can we write the full Encyclopedia Britannica on the head of a pin? Turns out you can. Can we build a motor the size of a fruit fly? Turns out you can, and much smaller. And these are actually images the following year after he gave his talk. These are images of that very small motor and the Encyclopedia Britannica written on the head of a pin. So they achieved this almost immediately with known methods for the time. And what this kind of spurred was this really amazing, let's call it silicon boom, because what they were doing was they were building these small things in a material called silicon. Many of you are familiar with this because your chips on your computers are made of silicon. And instead of vacuum tubes, when it came to building computer chips, we have something called a transistor. And effectively, because silicon is a semiconductor, you are able to manipulate the materials such that sometimes there's electricity flowing through this gate and sometimes there isn't. And when there is, it's a 1. When there isn't, it's a 0. And so the result of that is you can now have the same binary math that you had with your vacuum tubes, but very, very on a very, very small scale. This is a chart that shows Moore's law. The number of transistors you could fit on a chip doubles every year, except at some point will maybe reach a limit. This is what a silicon chip would look like. This is like maybe 100 chips on here. This is a 4-inch silicon wafer with all sorts of chips on there. And if you were to build a computer that had the same computing power as you have on your phone right now, but it was built using vacuum tubes, you would need to fill the entire Pentagon building in Washington, D.C. It wasn't until the 1990s that we had the first case of internet activism. These were the cypherpunks. You may have heard of them. This was an internet listserv where cryptographers said, hey, we need the cryptography tools that the US government has developed in order to make sure we have privacy on the internet. Why would you want privacy on the internet? Well, if you're sharing educational data, financial data, health data, you need to make sure that you're only sharing it with the people that you want to see it. Let's see. Let's click this. And then in the early 2000s, this might look familiar to you because this is the article that's actually in the Genesis block of Bitcoin. Chancellor on the brink of second bailout of the banks. You have the financial crisis. So all of these things taken together has kind of created a perfect storm. Basically our silicon innovations and getting really, really efficient small computers, our financial crisis with people being frustrated about central banking and the banks generally and how they behave, along with this advocacy for cryptography technologies to be released, all led to the perfect storm for something like Bitcoin to be released, the white paper in 2008, the code in January 2009. Um, and so Bitcoin was really compelling because unlike previous versions of internet money, of which there were many, in fact, the Bitcoin white paper cites a number of them, like B-Money, Hashcash, eGold, Bitcoin for the first time was able to run without any centralized third-party intermediary actually maintaining the transactions or the ledger. So Bitcoin is kind of like cash in that it's a store of value, medium of exchange, but it's really compelling because of the technologies that make it up. First of all, you have your wallet. And with your wallet, you have a public address where, although it does not identify you, you still have this notion that it's transparent. Anyone can see your account balance, anyone can see your full transaction history, and only with your private key can you actually send transactions from this wallet. See? Thousands of miners all over the world compete to add the transactions that you sign for to a block on the Bitcoin blockchain. A block just is some memory, and what's written to it is some transactions. It is generally labeled the highest block number that miner could find +1, and then it references the previous block, and then the miner will solve something called a nonce. So this is a cryptographic puzzle. Basically, the miner needs to guess a random number, but through that process, they actually spend electricity. Why would we want them to spend electricity? Well, it's cheaper to spend the electricity to only add one block than it is to spend the electricity to try to reverse 5 blocks. And as a consequence, you have this notion of immutability in the transactions of the Bitcoin because no one is reversing blocks. And by the way, if you're someone who is spending Bitcoin, you would not want your blocks to be reversed because then your transactions would be reversed and you would never use Bitcoin in commerce ever again. The other nodes on the Bitcoin network will express their acceptance of the block by building the next block in the chain. It's important to note that your signature is actually, your private key is actually your signature. And Satoshi Nakamoto, the creator of Bitcoin, actually defines a digital coin to be a chain of digital signatures. What do we mean by that? Well, whenever you receive Bitcoin, the data that you receive is actually everyone who's ever signed for that Bitcoin before. And so that Bitcoin is actually a representation of all of those signatures. That's very important because the miners are actually checking to make sure before they add transactions to a block that these transactions have not been previously spent. And this is how Bitcoin solves the double spend problem. This is what I think is the most compelling chart in all of crypto. This is the Bitcoin money supply chart. You can see the blue lines are the Bitcoin miners reward. Every 210,000 blocks, it cuts in half. It started at 50 Bitcoin. Then about 4 years in, it cut to 25, then 12 and a half, and it currently sits at 6.25. And the consequence is this red line, which is kind of cut off a little bit, but this inverse logarithmic red line is the Bitcoin total money supply, which, as you could see, has some type of scarcity. There will only ever be 21 million Bitcoins in circulation. And this is really interesting because this is one of a graph I thought was interesting when I was shown it in Econ 101. This is your index of central bank independence on the x-axis as a function of your average inflation rate on the y-axis. And as you can see, the more independent your central bank is from government control, the lower generally your average inflation rate is going to be. But there will always be a target inflation, even down around 2 or 3%. And so maybe that compare that to Bitcoin that has some type of scarcity. I think the intention behind Bitcoin was to have some type of deflationary currency. This is a Bitmain Bitcoin miner. And the reason I bring it up is because this actually brings us back to our discussion about the chips. Why? Well, in the early days of Bitcoin, you were able to mine using just your laptop. And then people started using gaming computer chips, which made them more competitive. And the Bitcoin miners then had to upgrade their chips to the gaming chips. And then Bitmain came along and built something called an ASIC chip. So these are specially designed chips specifically for Bitcoin mining. And effectively, those outcompeted all the gaming chips. Now, I believe Bitmain just released a Filecoin miner, which is really, really interesting. I think each one is like, I don't know, somewhere between 20 and 40 grand. But nonetheless, this basically speaks to the fact that we are constantly building these more efficient chips to be able to do the computing processes that we want to happen. What's interesting is that on the Bitcoin blockchain, the software is actually designed to understand when these chips get more competitive, and it will actually make the time it takes to solve the Bitcoin miner's reward, or the proof of work, basically that cryptographic puzzle, it'll make it much more difficult the more efficient the machines get. So effectively, the amount of time it takes to mine a block stays consistent at 10 minutes, but you still need to upgrade your chips because you are competing with other miners who will outcompete you if they have more powerful chips. In 2016, Ethereum came along, and Ethereum's major innovation is smart contracts. Thank you, Vitalik. Smart contracts on top of a blockchain. And the design of Ethereum really tells us what the purpose of Ethereum maybe should be. The blocks settle much more quickly, every 10 seconds, compared to Bitcoin every 10 minutes. Excuse me. There's no half-life. There's no scarcity in the money supply of Ethereum. And Ethereum is also now proof of work. Proof of stake, which we will maybe beyond the scope of this talk. But long story short, the idea behind Ethereum is to serve as almost the oil for all of the commerce happening with these smart contracts. Let's just skip ahead. Let's see how much time we have. I'll skip that. 5 more minutes. Okay. You remember I told you about your wallet being open and transparent. And from that, you could get a lot of very, very cool forensics. This is one of my favorite examples. A company called Elementus put this together. This is an initial coin offering called Car Taxi that claimed to raise $7 million. But you could actually look at the data available to you on the blockchain. And as you can see here, the 2 red dots with all the blue around it are the smart contract wallets. And this wallet right here is the Car Taxi Ethereum wallet. First of all, we know that this smart contract address is the Car Taxi ICO because Car Taxi announced it on Twitter. All those blue circles are third-party investors sending money to that smart contract. And we know this is the Car Taxi wallet address because even though wallet addresses are anonymous, well, if Car Taxi is saying, hey, send money to my smart contract, the smart contract would only ever forward that investment to the Car Taxi wallet. And so from that, we have figured out who's who effectively on this blockchain. And you'll notice in the second round of the ICO, something bizarre is happening. Car Taxi is sending themselves some money. And so the result, actually, when you parse through all the data, is that from third-party investors, Car Taxi only really raised $2 million, but they sent themselves $5 million. Why would they do that? I don't know. Maybe in a speculative market, they want to make it look like more people are interested in their investment than actually are, and this is maybe some type of fraud. Who knows? So that is a story with what you're able to do. This is a Bitcoin Genesis block, the raw hex version. You'll see that article I mentioned earlier is in here. And this tells us actually you can include text in your Bitcoin transactions. And so what's actually happening now is this new thing called inscriptions and ordinals on Bitcoin, where people are actually labeling all of the Satoshis on Bitcoin. So Satoshi is down to the 8th decimal. And more or less, this has created a secondary market. Why label the Satoshis? Well, maybe you're a collector and you want to own a Bitcoin that was once owned by Satoshi, or that was once used in the 10,000 Bitcoin for 2 pizzas transaction. These are all things that maybe would make one Bitcoin more valuable than another Bitcoin. And so there's a whole secondary market for Bitcoins with these inscriptions and ordinals. All right, that brings us to Filecoin with 3 minutes and 55 seconds left. So I told you all about crypto, and you might say, okay, that's interesting. I'm here to learn about Filecoin, and I'm going to tell you a bit about it. First of all, your IP address on your computer actually uses something called geographic addressing. And what this means is it's very inefficient to fetch data on the internet because you're effectively pulling from geographies and giving directions as if it's literally raw geography. And so on Filecoin, we look to something we think is more efficient, the ISBN system in your library. So every book that's ever been published has a unique identifier called an ISBN number. And this ISBN number tells us something. It's self-describing to the book. For example, it'll tell you about the book's genre. So we have a system that is called content addressing, and every file added to Filecoin is content addressed. What does that mean? The file goes through a hashing algorithm, and it computes a unique identifier called its content ID. If you upload the same file twice, you're going to get the same content ID. If you make even the smallest change to a file, it changes the content ID. And for this reason, a social impact partner called Starling Lab actually uploads their evidence of war crimes that they go around to Ukraine and Bosnia to take this evidence and create dossiers that are submitted to the International Criminal Court. They actually upload this data to Filecoin to make sure when they submit it to the court, no one has tampered with that evidence as it sits there, because the content address of those files would change. We also organize these files on the platform the same way you would organize your photos on your computer. We organize it into folders, basically, and we call this data structure a directed acyclic graph. So for the computer science students in the room, you'll be familiar with graph theory, but effectively your folders and your pictures are the nodes, and the edges tell us the relationship between those folders and those pictures. And because it's directed and acyclic, it gives us a number of interesting features. Deduplication is an example. For example, you have the same picture in 2 different folders. You need not show it twice. You could simply have those 2 folders point to that one representation of the file. You also have recursive nature here that makes it easy to traverse multiple times. And you need not get an entire DAG to get just a subpart of the DAG. It's important for me to mention IPFS, although it's a different platform. IPFS is a hypermedia protocol that allows you to share information that is compliant to content addressing and this Merkle directed acyclic graph that we call interplanetary link data, but it is not the same as Filecoin. There's less of a assurance that your data will be there a long time from now because there's no marketplace to make sure people are paying for their data to be there. And that's where Filecoin comes in. On Filecoin, as you've heard here many, many times, what your Filecoin process more or less looks like. That's our 20 minutes, but I'll maybe take 2 more minutes. Cool. What our Filecoin mining process looks like is step 1, someone with some data that they want stored on Filecoin says, hey, I have this amount of data. I want to store it for this period of time. This is how much Filecoin I'm willing to pay to actually store it. They propose that as a deal on Filecoin. And then a miner, and by the way, the data that they're storing is compliant to the content addressing I just described. And then a miner, if they are interested in taking that deal, a storage provider, will say, hey, that's a really interesting deal. It makes financial sense for me. I'm going to do a proof of replication to demonstrate to you that I want to accept this deal and I've made a copy of your data on my data center. And then every day after that, the storage provider will provide a proof of space-time. What is proof of space-time? Well, it's a cryptographic proof where the storage provider says, hey, I have your data in my data center at this period of time in this, literally in this memory space. And if the storage provider does not show that proof of space-time, they actually get penalized by having Filecoin slashed from their wallet. And then at the end of the deal, these deals are time limited. At the end of the deal, the client can decide to renew or to find a new storage provider to work with. Okay. We'll skip that. Okay. All right. We're building many things on top of Filecoin, FVM being one of them. So FVM, as you heard from Sarah and Longfei yesterday, is on-chain programmability. It's smart contracts on top of Filecoin. Why would you want that? Well, maybe as an example, you write a smart contract that is for perpetual storage. What would that smart contract look like? Well, you would endow the smart contract with some Filecoin that's invested somewhere, and the business logic of the smart contract would be, hey, if this endowment made more money last year than the Filecoin deal would cost next year, renew the deal automatically. If not, find a new storage provider. You could also do file access control with smart contracts, where you control which crypto wallets actually have access to certain data that's stored, or you could do a data DAO where you could have smart contracts manage the governance around some set of data. Okay, I think I'm out of time, but with that, happy to answer any questions, and cool.